going to introduce a person who is having more than 18 years of experience in design and development of mission critical software for underwater weapons and autonomous underwater vehicles. And his major contributions are development of bootloaders, device drivers, and board support packages for Intel 486, PowerPC and ARM processors based single board computers, design and development of real-time embedded software for heavyweight and lightweight torpedoes, development of mission software for autonomous underwater vehicles AUV, established end-to-end AI infrastructure for development and evolution of deep learning models, development of deep learning based AI models for underwater mine detection and classification in camera and side scan sonar imagery. And he awarded and recognitions by Silicon Medal on National Science Day in the year 2010, Technology Group Award in the year 2016, Laboratory Young Scientist of the Year Award in the year 2017, Silicon Medal on National Science Day in the year 2020. And he's a post-graduation in Computer Science and Technology from Andhra University. Now he's serving as a group head, Embedded Software Group, Embedded Systems and Instrumentation Directorate. He's none other than B. Suresh Kumar, scientist in Computer Science and Software Group, Embedded Systems and Instrumentation Directorate, Naval Science and Technology Laboratory, Ministry of Defense, Vigyan Nagar, Visakhapatnam. Now I would like to request our speaker, B. Suresh Kumar sir, to speak few words about this gathering and hand over the sessions.
First of all, my sincere apologies for being late. I got stuck in the traffic jam. Just first thing first, don't expect anything, like any explanation on any algorithms or theoretical aspects. Mostly I will be discussing on the practical implementation of deep learning algorithms, particularly in resource constrained systems, specific reference to embedded systems being used in defense applications. So I'll be mostly showing the journey which we followed during the course of last 2 years for implementation of these deep learning algorithms to identify and classify underwater objects. So So the outline of my presentation would be basic introduction, followed by the key components in deep learning, or all the main things that constitutes deep learning. Then the deep learning pipeline, how from the data we gather to the inference we do, what is the flow over that, and how to engineer a data for the deep learning model training. Then the deep learning model selection, different criteria to select a particular model for a given use case. Then different aspects on model training and evaluation. Then brief on the deep learning R&D, what we are currently doing at NSTL. Then I will be showing one case study in which we have implemented this deep learning based underwater object detection algorithm. Then we will go for the conclusions. I think this swiping yeah I think yes. Long swipe, okay. This is just for sake of the continuity I am showing, because most of these things might have already discussed in the previous classes. So this AI, that is particularly artificial intelligence, is not a new technology. It has been there since 1950s, but it is taking a different shapes or different forms based on the evolution in the technology and the availability of data. Then during 80s, and up to 2000 it was in the form of machine learning. Now we are in the deep learning era. So why artificial intelligence is so popular now? So it's basically due to the availability of large data and the availability of the compute that is which is able to process this large data to make some inference on that. So these two things are now fueling the deep learning. So coming to the various applications, we have right from like industrial applications, then application in fundamental sciences for drug discovery and social governance and cyberspace. So we have a number of applications. Below that we have different layers like perception layer, cognitive layer and decision layer, which will be actually driving those application layer. So the underlying things are the data, the computing, the machine learning algorithms and the framework, because without these things we will not be able to achieve the artificial intelligence. So for that we need the data, the processing or the compute and the different types of algorithms to solve a particular problem statement, and you need a framework to do all the things at a place. So that is like shown as the key components. That is data, your algorithms which work on the data, and you need some frameworks which will actually be running those algorithms, and on top of the actual hardware all these things will be running. So these four things are the main components of any AI or specifically any deep learning system. So coming to the data, if you see the statements given by Clive Humley, it was in 2006. So he predicted that data is nothing but new oil. Like in the olden days when electricity was like invented, that is, tremendously impacted the industrial revolution. Similarly, he predicted that data will be the new oil, which will be fueling the many innovations. Exactly after 1 decade, Andrew Yang, a popular scientist, he said that AI is the new electricity now. So if you see the different machine learning models, they have almost saturated. So the main thing that is driving is the data. In fact, Mr. Andrew Yang, a couple of years back, he started one competition. Like you take any model, but you manipulate the data and get the best result out of that. So if you see that models, deep learning or machine learning model, they are saturated now. So based on the data, now your model accuracy is actually varying. So if you see the who is producing such huge data now? Like every minute or every second we spend on social networks, between YouTube or Netflix or whatever platform, those things are actually making money to the most of the technical giants, tech giants like Google, Yahoo. So like every activity we perform on the web is creating a lot of data. So that's how the huge companies like Microsoft, Google, they are able to produce more sophisticated systems because they have the abundant data with them. So if you see why now deep learning is so important, because we have traditional algorithms like machine learning algorithms, they don't really scale up with the data. As the amount of data increases, their performance plateaus. So we need to go for even better algorithms like neural networks, and then comes the deep neural networks, which are very efficient to learn the intricacies or the different patterns in a given data. That's how they are able to achieve more accuracies compared to the machine learning algorithms. This is what I was mentioning, the difference between the deep learning algorithms and the older machine learning algorithms. If you see the big industry giants, they have the high data. That's how they are able to maintain that gap between small and medium sized companies. So because they don't have enough access to the huge data. So it's an iterative process. The more data you have, the better your AI model will be. Then you can develop better products. Then more users will be using it. In turn again you will get data from the more users. So that's how, like, if you see the companies like Tesla, where they have like millions of cars on the road, like every day they get the real-time data from the these self-driving cars. That's how they are way ahead compared to any other autonomous driving companies like Waymo or any other companies. So data is very much important. So the quality of data directly impacts the performance of your underlying machine learning or deep learning model. So what affects the data quality? It's not only the data we gather, the process which you follow and the tools you use, and the workforce, which the people who actually annotate the data. If you see any supervised learning algorithm, we take the data, we do some kind of labeling. So if we take up any particular object detection algorithm, we need to manually draw the bounding boxes around that object. So the quality of bounding boxes also defines the quality of your performance of your machine learning algorithm. So the workforce needs to be properly trained, and they need to be more patient. Like if you see Tesla, they employ more than 1,000 engineers just for annotating the data, and they do at the 3 levels. So 2 independent teams they annotate, then those things are again supervised by the 3rd team. So any 1 or 2 wrong annotation in the huge data set will completely change the behavior of the any deep learning algorithm. So these things are very much important. You need to have some high quality labeling tools, and you need to follow specific or very systematic processes to maintain the data, because data will be generated over the period. How you accumulate over the data over the period and combine them to train a model is very, very important. So actually the 80% of AI product time is spent on data preparation and engineering tasks. Rest all your model building and all, they're like very, very less. The effort required to that is very less compared to the data preparation time. So coming to the second important thing, the algorithms. Like we have many deep learning algorithms now, right from classic neural networks to GANs, then deep reinforcement learning and autoencoders. There are so many algorithms are there. These algorithms, like we select a particular algorithm based on our like different problem to be solved. So there are the important things to be considered to select any object detection algorithm specifically. Like one thing is the accuracy and performance levels. Generally accuracy is measured in terms of MAP, that is mean average precision, and also you need to consider precision recall also. The recall is more important when you don't want to have like false positives. Then inference speed also important. Because once you submit one new data to any model, it should not take longer times to give the inference results. So that is also an important criteria. Then the resource requirements, like how much the actual model size is, like whether it will be fitting into a given platform where we are going to deploy this model. Then the training time also very important. If you see with like most of the state-of-the-art models, they train on months together, like on bigger image, image data sets like ImageNet and all. So training time is also very, very important, because that has direct impact on your resources, like power consumption and heating issues, all these things. Then also the deploying platform. That however good your model is, if it is not fitting into the platform where you are finally going to deploy, then it's of no use. Then you need to consider the application and dataset size also, like the number of classes in a dataset and their complexity, and the data availability and quality of the data, and the customization and transfer learning also you need to consider. Then the other additional requirements are like when you want to develop a model, select a model, whether to go for a open source or openly available models, or you want to develop a custom model from the scratch. Then support of community, like when you are stuck with something, whether there is any open source communities available to help out, that is also an important thing. And also another important thing is the ethical considerations, particularly for medical applications. Then there are coming to the popular object detection models. Basically, we have particular object detection. We have two types of models, like two-stage models and single-stage model. Where the two-stage model are they're all proposal based, like RCNN, fast RCNN, those things are available. And then for single-stage models, we have YOLO and SSD. They are all the widely used models now. Because if you see the two-stage models, they have the initial first stage, they do the proposal, they generate the proposals, and the detection happens in the second stage. So they are very accurate compared to the single stage models, but they take more time to do the inference part. Whereas single stage model, in a single pass they will be able to do the detection or classification task. The most popular thing is now YOLO. And for small models, I mean for resource constrained devices or like mobiles and all, if you want to use, you can go for SSD, like single start detector. So there is no one size fits all kind of solution. The best model depends on the specific use case, obviously. So just if you see the history or different versions of YOLO, it started from 2015. Where the YOLO version 1 has come. So that has won the object detection challenge in CVPR in the year 2015. That is developed by Mr. Joseph Redmond. Then followed with different variations. Now the YOLO V8 is there. Like there are different versions like YOLO X, R, S. So many variants are there. And the PP YOLO is like Paddle, which is a Chinese company from Baidu. And particularly in YOLO 5, again you have different variants, like small model, medium. Basically they define the network size. The smaller the network size, your inference speed or processing speed will be faster, size will be less, but again your accuracy levels will be not so great. So you need to consider it's a trade-off between the accuracy and inference speed. So based on that you can select a particular model. So again the same thing, if you see the different models, the parameters, if you see the millions of parameters, the YOLO extra large model is almost like 86 million parameters, but your accuracy is high, like 68.9 it gives. You see the inference times on a typical CPU, it is like 766 milliseconds, like almost like 8 seconds it takes. If you take the GPU, the time is almost like 12 milliseconds. So these are the typical performance parameters on CPUs and GPUs. So coming to the frameworks, like once you decide a particular model and you have the data, now you need to train this model and the data in a particular framework. Then you have to select a particular framework. There are so many frameworks available, right from Cafe, then Microsoft Cognitive Toolkit is there, MATLAB is there. The most popular things are now PyTorch and TensorFlow. Most of us know that TensorFlow is from Google, PyTorch is from Facebook. So both are open source models. So initially the TensorFlow was more popular. Then PyTorch came somewhere around 2018, but it is very quickly catching up. Now, most of the research community, they go for PyTorch because of its debugging capabilities. So if you just compare both of them feature wise, you see that ultimately the underlying neural network is a computational graph. So TensorFlow goes with a static graphs basically. So which freezes before it goes for further this thing. So that makes it not so great for debugging things. If you want to debug the model in different layers in different stages, in TensorFlow it is not possible. But because of dynamic graphing, PyTorch it is possible. Then the learning curve, if you see, TensorFlow is moderate or a little bit higher side. But PyTorch is easy because it looks more like Pythonic because it is built on top of Python based library. So if somebody is good at Python, they can easily understand PyTorch models. That debugging I have already mentioned. The performance wise, they say TensorFlow is high, but PyTorch is also up to there actually. So I think this is wrongly mentioned. Mostly industry and the deployment, I mean the industry level people are using TensorFlow, whereas researchers are using PyTorch. There is a mistake in this. Then coming to the hardware, I mean once you have the three things now, data you have, the model you have, and you selected a particular deep learning framework, then ultimately these three things should run on a particular machine. So we need to select, we have basically two options, whether you can go for a cloud-based service, where you can subscribe from either Google Colab or Amazon AWS, Microsoft Azure. There are so many players are there in this field. Or you can have your own hardware, expensive hardware like NVIDIA DGX server, which will have a A100 or H100 kind of GPUs. But again, there are different choice things are to be made. Like if you have some kind of very sensitive data, like if you see the defense applications, because if you want to run in cloud, you need to upload all the data in the internet. So in defense, where we are not allowed to do that, so obviously we cannot go for cloud-based service. So then we have to go for in-premise kind of hardware. So both has got their advantages, drawbacks. So like small companies which, who cannot afford kind of this kind of machines can go for cloud services if their data is not sensitive. So again, just to compare between CPU and GPU, like why always we use GPUs for model training? Why not CPUs? CPUs are basically designed for like sequential applications, like you fetch the code, then piece of code, then you execute by taking certain kind of inputs. Because they follow a sequential process, and they're like where you require a quick processing task that require interactivity. All these things, CPUs are optimized for that. But GPUs, because CPUs cannot do parallel processing, because they have to do a sequential. But whereas GPUs, they can have like hundreds or thousands of cores to like do parallel processing. If you take any image and you want to do some kind of convolution operation with some let us say some 640 by 640 with 3 by 3 kernel kind of thing, in CPU you have to do sequentially. But if you have multiple cores with GPU, so in single clock cycle you will be able to do the complete convolution operation. So that is the advantage with GPUs. But again, most of the training or inference happens at GPU, but initial data pre-processing and the post-processing we do in CPUs only. Because this is the operation where it would take a lot of time basically. So if you see the latest GPUs, people who are using for training their large models, the latest one is that H100 from NVIDIA, that is Hopper 100. The earlier one was A100, which is Ampere architecture based GPU, which is 6 times better than A100 basically. But again, cost, it's like a beast. We need to spend a lot of money on that. There are majorly two players now in the hardware space. One is NVIDIA and AMD, but NVIDIA is the market leader now, with the different kinds of hardware as well as the software, like CUDA, like Compute Unified Device Architecture, and here are the different libraries which basically accelerate the computation. So AMD is still nowhere near NVIDIA. Which one? NVIDIA is always preferable. Yeah. So that is about the training part. Like when you deploy on a particular device, you need to have again certain hardware elements that we call inference hardware. So if you go for low power kind of inference hardware, again from NVIDIA family, we have different kinds of systems, like we call it a Jetson family, right from Jetson Nano, then Jetson Xavier, Jetson AGX. So it's like a small supercomputer. If you see the Jetson Nano, it's almost like a 0.5 terafloating operations per second. And it is on the size of a credit card actually. So small. Then next we have Jetson TX series, which are now obsolete now. The NVIDIA stopped support for these modules. The next, the middle level is Jetson Xavier NX, which is almost like 6 teraflops. Then the bigger one is AGX, basically up to 32 teraflops we can go. Again, it draws almost like 30 watt, and this draws around 15 watts power. You see other things from Google. We have TPU, like tensor processing unit, which has not become so popular, but still many are using that. And then in Raspberry Pi, we can use certain from Intel we have certain kind of accelerators. Then from OpenCV we have Oak and OakD platforms. So just to mention few salient features of Jetson Nano. So it comes with a CPU also, a 64-bit quad A53, which runs at 1.43 gigahertz. And it all in a as I mentioned, it is so small, like it is the size of credit card actually. This is the carrier board and with heatsink. Then we all 4 GB memory, all these things are inbuilt. Then the next one is the Jetson Xavier NX family, and all these modules comes with again additional peripherals like Ethernet, UART, GPIOs. So many things are there. And then the latest entrant in this market is from Xilinx. Xilinx is traditionally known as FPGA based company who would produce most of the FPGAs, but now they have come up with a specific system on module for machine learning applications like Kriya KV260 board, Pascal MP SoC as a base compute element. On top of that, it has 128 core Maxwell GPU for video and graphic processing, and it is comparable with Jetson Nano. Power is also around 15 watts only. But again, here the challenges are like most of the openly available models, they straight away run on NVIDIA based platforms, because most of the people are using. But if you want to go with the FPGA based systems, you need to do certain kind of modifications in your networks, because not all network features are supported in FPGA based systems. So these kits are very good to start with any machine learning and deep learning applications if you want to develop. Then because you have the ready reference of different kinds of models, which is already ported on this hardware. So you can always pick up one model and start developing on your own application on top of that. So coming to the deep learning pipeline, so it starts with the data collection. The data again depends on the different domain. Then once data is there, you need to clean the data, maybe format the data. Once that is ready, we do certain kind of data augmentation, because it's not always possible to get the data in different or orientation or different conditions, different climatic conditions. So we apply certain kind of augmentation techniques to just increase our data set size, like traditional methods like position changing, then coloring, scaling, cropping, or some copy paste augmentation, rotations. Those things we apply. Once that is done, we do labeling. It is a supervised algorithm. Most of the image processing algorithms are supervised only. So we do bounding boxes. Then we do annotation. After that is done, we have to split this data primarily into 3 sets: train, test, and validation. Because the test, whatever data you to test, that should not be part of your training data. So to evaluate or to validate your machine learning algorithm, you need to split this data. Then next is our hyperparameter initialization. Like you need to select the learning rate, what kind of optimizer you use, then how many number of epochs you want to train, all these things. So once model is trained, we prune the model to reduce its size. That in later part of my presentation, I have one slide over. Then ultimately we'll deploy the model. Then we do the inference or we do the evaluation. If it is meeting our performance requirements, well and good. Otherwise, we need to again follow the same chain. Or whenever you are getting new set of data, you add that new data to your training and do retrain that again. Same flow follows. Now coming to the deep learning R&D that's happening at NSTL. Just to set the context, I will be just explaining what are the different domains of research at NSTL and how we can apply different machine learning or deep learning techniques to enhance the performance of existing systems. So in NSTL, there are different domains. I think except civil engineering, all branches of engineering is there, right from hydrodynamics research, where the people will be working on the different shapes of the ships or submarines. Then we have propulsion technologies, like electrical propulsion, we have the thermal propulsion. Then control guidance and navigation group, where they design the control and navigation algorithms. Because ultimately most of our weapons or systems, they work in autonomous mode without man in loop. So they design those algorithms. Then embedded systems and instrumentation, where people handle different kinds of sensors, data acquisition, and implementation of these control and guidance algorithms on the embedded hardware. Then the vapor fire control system, like before firing or launching any vehicle, we need to do certain kind of health checks, feed certain kind of parameters, how the weapon should go, how the vehicle should move. So those things will be handled by the weapon fire control systems directorate. Then we have countermeasures, like when your own ship is under threat, how to escape from the threat. Like if enemy fires some missile or torpedo, just to buy some time to escape, we fire some kind of countermeasures, so that mimics the our own ship's signature, so that our ship can escape and that enemy torpedo or missile can home onto that. Then also we have homing systems. Basically it is like equivalent to radars, like we have homing seeker systems. So if you see where we can apply this AI, actually there is scope to apply everywhere. There is no field where you cannot apply AI techniques. So because we generate a lot of data, always we can use the data to improve the performance of the existing systems. So why AI is important in defense applications? Basically to make them more intelligent, because they are autonomous in nature. If you equip with the AI algorithms, they do better decision making, and they certainly reduce the human in loop. There are a few things I want to mention, particularly because my case study or application which I am going to explain in my next slides will be based particularly on mine warfare. If you see mines are like underwater mines, they are used like defensive weapons. Either torpedoes or missiles, they are like always fired against ship or enemy ship or submarine, like they are like offensive. But these mines are laid along the coast of our waters, just to protect our own waters basically. They prevent the enemy ships or submarines to come to our zone basically. So during war scenario, when our ships wants to move to certain particular coastal zones, we need to identify the mines basically. So the two things or two approaches that people employ are mine hunting and mine sweeping. So in this manual process, what people do is they go with ships, they employ certain kind of sensors to see whether mine is present or not, so that our own ship can pass through safely. So the major drawback is man in loop. So sometimes they get explored because of the influence of our own ship. So to avoid those things, we can always employ some kind of intelligent systems on autonomous underwater vehicles. They can go on their own, they can autonomously detect and classify mines and give the feedback. So we can neutralize them or we can avoid that path. So autonomous underwater vehicle, sir, now the widely used things now, they are coming up for autonomous detection and classification of mines. We see that traditionally automatic target recognition approaches. So people are using pure image processing based techniques just to detect edges and corners, but they are not giving enough confidence to the user, because in underwater scenario mostly we employ acoustic sensors, and they don't give the images what we get is not like optical images. So it's I will be showing those images. They will be very filled with a lot of clutter. So by employing pure image processing techniques, it's very difficult to say whether the particular image is a mine or not. Then came some machine learning approaches for feature extraction and classification. But if you see the latest happenings like deep learning, where they can learn on the training data, they learn the complex features or combination of features, and they give the better accuracies. So this, just to give a brief introduction, like some 1.5 years back we got one project where Navy wanted a small AUVs, like man-portable AUVs, a single person can carry and deploy in a particular area, which can detect and classify and destroy the mines. So just to give the better understanding, I have one animation. You can go through this. Sound is not there. Okay, sound is not there, no? Okay. So it's only like concept of operation basically. So mostly mines are deployed by submarines in a particular zone. So now submarine is deploying the mines. Now these ships, actually our own ship wants to pass through a certain area. We don't know whether or you have the intelligence that particular area is mined. So we want to identify whether that area is mined or not, so that our own ship can pass through safely. So what we do is, first they take particular area, they segregate into sub areas to do the search operation. So before launching the AUVs, we need to program the AUV, that's the FCS, the fire control solution which I was telling. So we are feeding the AUV with a certain area map basically where it needs to search. So out of 10 kilometers square, we are taking 1 kilometer square. So multiple AUVs are deployed. So these AUVs work in tandem, I mean in the swarm mode, that's what you call. They communicate each other. They ensure that the given area is totally covered and no area is, not explored. So they go in tandem. They employ basically cameras and side scan sonars to do the detection. So once they reach the location, as you know that underwater GPS doesn't work. So every time we need to, periodically we need to come up to correct our position. So they detect the mine, and the AUV which detects will come up and pass on the data to the mothership. So other AUVs will be continuing their search. Once it passes on the data, again it will come and join other three to complete the search basically. So this we call as course search. So once the particular area is completed, all the AUVs will be taken back, or one of the AUV will be again deployed to do the fine search basically. In fine search we use optical camera basically. Typically these cameras underwater will not have more than 5 to 10 meters of range. So that cannot be used for coarse search. So once it is localized, that position is noted down, and the same thing is informed to the mothership. Then all the surveillance, we call those things as surveillance AUVs, those things will be launched. So this neutralizer AUV is equipped with explosive basically. And if you see the typical mine, they are in the order of 600 to 1000 kgs. which cannot be destroyed by the small AUV, which is of 30 kgs, which can carry only 4 to 5 kgs of explosive. So what we do is we try to destroy the sensors, so which will make the mine ineffective. So that is the basic idea. Now this is the requirement given by the Navy. So how we have approached to develop this system. So as a basic introduction, like side scan sonar imaging, if you take, like yeah. If you see, because these small AUVs, they move very slowly, like in the order of 4 to 5 knots. So to cover a 1 square kilometer, 4 AUVs takes not less than 2 hours. Because your side scan sonar has got limited range. In the order of, if you using even low frequency, they may be hovering at the most 100 meters. So at a time, one AUV can scan 200 meters only. And you need to cover. And if you see the any AUV, side scan sonar we call because the sensors are fitted either side of the AUV, and bottom part will be like blind zone. So in next run, you have to cover this blind zone also, because in a particular given run, it can only see the side towards sides of either left or right, and the bottom part will be again it cannot be seen. So in your next run, once you turn back again, you have to need to have that overlapping zones. So it takes a lot of time, and if you see seas, there will be a lot of underwater currents. So it's a very time taking.
During fine sense you told us. During that fine sense, there is no threat for that own AUV.
Yes, actually that is a sacrificial AUV. Yeah. It will go with the explosive, because already surveillance AV has identified a mine in a particular location. You have the precise location. Again this AV will go to the locations, again reacquire the mine, then it will explode. So with that explosion, the sensors fitted in the mine will be destroyed, or it will become ineffective. So ultimately that mine is like a dead weapon. So it's not like optical image. If you see any acoustic image, it looks like that. Basically what happens is, any side scan sonar transmit, because they are all active sonars, they transmit a ping and they receive the echo basically. So once it transmits, the transmitted ping will hit a particular object based on your transmission angle, all these things. So the echo will be mapped into a pixel value. So what we do is, each transmission we collect the pings, we accumulate the pings, that we convert into grayscale image and construct an image. This is one challenge basically. So you will be seeing the shadows. If you see this particular object is illuminated from this side. So because this is a metal object, you will have the more return strength. The ray or the ping that hits here will have the more energy reflected. So that's why you can see like highlight. And the one which is not illuminated looks like a shadow. So basically we are looking at the shadows only. It's not like optical imaging. So this is the optical image of a underwater mine. If you scan with side scan sonar, it looks like this. And again the shape or the length of shadow again depends on your height also. So always we cannot say that this is the mine of this thing. Even sometimes it may misclassify rocks also as mine, because obviously because it is looking at the shadows only. So any rock, there is chance that it may look like mine shape. We are only looking at the shape. So there are different challenges, like how to avoid the false positives. Side scan sonar, typically they operate in dual frequencies. Like low frequency, something around 600 kilohertz, they give maximum 40 meters. They give up to 100 meters. The high frequency in the order of 1200 kilohertz, they give mostly 40, not more than that. 40 meters. Yes, sir. But resolution will be high, because higher the frequency, your resolution will be better, but range is less. So in lower frequency you will get better ranges, but lower resolution. That is the trade-off. So generally what our team does is they use, traditionally they are using Kalman filters only. They take the speed because they will be doing dead reckoning. You see over the air you have the GPS speed, everything is coming. So obviously you will be getting positions and speeds. But in underwater, initially we take the fix. Once we go underwater, we purely depend on the velocity of the vehicle. So you know the velocity and you know the orientation, like roll pitch we have. So based on that, every time step we estimate by using Kalman filters. But what happens is over the period, because of this integration process, you see any integration operation always you get the plus C kind of thing. So that will be accumulated. So every time you are accumulating certain kind of uncertainty. So if you are running over a long periods, your drifts will be more. Like if you want to go to the x1, y1, but you will go to x1 plus some delta. So to avoid that, always we try to come up intermittently, maybe around 15-20 minutes. Based on our simulation result, every 15 to 20 minutes you need to come up, take the GPS, correct yourself, and again dive again. So this is the traditionally used method. Or now people are employing some surface vehicles, small surface vehicle you can have, because underwater AUVs will be running, the surface vehicle will be running on the surface, which will have direct access to the GPS, and it can have acoustic communication modem. So it will be giving real-time update to the underwater AUVs running underwater. So they need not come up. So there are systems like ultra short baseline, like USBL systems, which can be used to fix the positions of the other systems. Because we cannot use any RF based system underwater. Yes. Yes, yeah. That's why what we do is, in return path we cover that area, overlapping. So what happens is, like it follows a certain path, no? No, because we are using not ship, we are using AUV, so it will cover certain zone. In return path, we make sure that the other part of this thing is covering this gap. Ships, that's why initially I mentioned, ships they go, there is a danger. It may explode also, yes. But people are using like mine hunters, mostly made up of non-metallic parts. Because these underwater mines, they work on different influences. Like one is the acoustic, because as the ship comes near to the mine, your acoustic signature varies. So mine will have its own intelligence to detect that acoustic signature, plus pressure. When the ship comes over on that, it will exert some kind of pressure, plus magnetic signature. So primarily these three influences are used to trigger the mine. So because small AUVs, they won't have that much influence on that. But when people are doing manual operations, they use small boats like mine hunters or mine sweepers, but still there is a danger. So, and it's a very laborious process. That's why the new trend is to go for low cost, small man portable AUVs, deploy multiple numbers, and they quickly scan the area. Even if you lose one AUV, the other AUVs will be able to do the task. That's the thing. Now at present, traditionally we were using like something like this energy or period kind of thing. Energy detection only we were doing, because if you transmit the signal and receive back, that reflections from sea bottom, rock and metal will be different. So you can put certain threshold and to filter out, and consistently you see and compute the energy over that and detect. But they are not foolproof. Not with image processing. Now at present in this application, what we do is we have used a traditional, not traditional, like openly available models only. Like there are certain models for people detection or some vehicle detection. So what we did is we have taken the same model, but tried on different data, like side scan sonar, mine data basically. So that I have few slides on that. So because this is small AUV, we cannot have gap pillars. Otherwise, in bigger AUVs you can have the gap filler which will be covering this dead zone also. So again, as I mentioned, data is very important. So we need to collect the data. So what we have done is, we have remotely operated vehicle fitted with side scan sonar. So we deployed these mines in our water tanks and harbors and a few lakes also. Then we manually scan those areas and collect the data, because we need to first build up the data set to train our model. So we collected data from camera as well as side scan sonar. So that data we did certain pre-processing, then we did augmentation, then annotation, then the data is split into train and valid and test sets. Then like traditional, there are drawbacks with traditional augmentation techniques like copy-paste augmentation. So those were not giving the enough accuracy levels. So what we did is like synthetic data generation. You have certain amount of data, you employ some deep learning algorithm which will learn from the data and generate artificial data or synthetic data. So this work is jointly done with IISc Bangalore. So what we did is we have employed denoising models, denoising probabilistic models. Basically what this model will have is, it will have two steps or two phases. In forward phase, what it does is it will take any training image and it will add certain amount of noise to the original image. So that noise is always like it follows the Gaussian noise. So that process is done till the complete image becomes a noise. So in this process, a neural network learns how the original image is getting transformed into noise. So what happens is, then randomly pick the noise out of the distribution and do the reverse process. Then you'll get the images, a totally new image, which is not there in this thing. Like if you see certain websites like the person that doesn't exist.com, so where the models are trained and use human faces. Every time you run, you get new face, the person which doesn't exist actually. Yes. So basically to generate new images, because practically it is not always possible to get the data in different scenarios. So this is one technique we have employed, like for training and sampling. So every time you sample, always it takes a noise which follows a normal distribution. From there it generates a new image. But again here the critical thing is it is very sensitive to the hyperparameters, the number of training samples and the variance of we need to precisely define the variance in that distribution. So if you see the data, these are all the actual images, these are all the synthetic images. They are very close actually. Otherwise earlier what we used to do is, you just rotate the image or crop the image and paste into different orientation. That were not so accurate because when you copy paste on image or an object and image, you will have the boundaries. So that was giving a lot of inaccuracies in the model. So we trained this model for 1000 epochs, which took I think more than 4 days in A100 GPU. Very time consuming process, but which is giving very good results. So this is how we split the data. We collected data in different sites. Basically this is NPOL, is one of our sister laboratory in Cochin. From there we got few data samples. Then in our own tank, we have one tank from harbor. So all the data we have taken and we split into train and testing. So this is the the size of data set. Again always comes the question, because we always say deep learning models requires huge data set. Like how much data is enough? But in literature they say at least 10,000 samples and each object should have minimum 1500 or 2000 kind of annotations. But still this is in the work in progress, we don't have that much of data. I think it takes for certain amount of time to reach that point. So now at present we are operating with these kind of images, but still we are getting good accuracies. This is the training results. We have compared two models, trained over 300 epochs. So we are reaching almost like 80% of MEAP. So what we do is, once the model is trained, we see the accuracy levels. then inference time also very important for us. Once we deploy that in our actual hardware, how much inference time we are getting. This TensorRT, I have one slide about that. I'll explain that. Again, that is on a two different types of models. This is on two different types of data set. One is one data set one is pure images without adding the synthetic images, and data set 2 contains actual images along with synthetic images. So we could improve the MAP considerably after adding the synthetic data. So ultimately, because the vehicle which we are developing is less than 30 kgs, and the space available for this hardware is very, very small. So our model cannot afford to have high-end hardware. So what we did is we developed our own custom carrier board at NSTL. Obviously fabrication is done by outside firm, but total design is ours. So this is the model on Creosome used for doing the basically vehicle navigation control tasks, whereas the deep learning model is running on Xavier NXOM. Then that is about the side scan part of it. But before we had access to the side scan sonar, we started exploring on open source data, because that time we were not having any underwater images. So we started our work, because NSTL basically was known for like embedded systems, all these things, but there was no team which was working on deep learning or ML. So like 1.5 years back, something we have started. So to start with, we have taken open source data and open source models and started basically to learn. So this is one video where we did training. This is brackish dataset openly available, because our model, if you see underwater, the images looks very small. I mean, object looks very, very small. So just to see whether the YOLO5 kind of model, whether it will be able to detect small objects in the cluttered environment. So to validate that, we have used this data set. It is giving good results basically. We are not using the model as it is, we are doing certain kind of tuning. Then what we did, we have collected the mine images and combined the data with the underwater image. So this is the performance. Our goal is that it should not classify any of those things as a mine. So it is not giving any kind of false detections. This is just to evaluate whether the openly available models are suitable for our application or not. Then, because there are all static images, means we recorded the video, we have taken frame out of that, then trained the model, and new video we did the inference part. But actually our vehicle will be moving dynamically. So that time our vehicle was not ready, so we did one experiment on the small jet board. Because your object is stationary, but your vehicle is moving. So just to simulate that thing, still it is giving enough accuracy levels. So then the same thing is tested on drone also. Same algorithm fitted on that one Jetson board, which is fitted on top of the drone. Then we did some kind of detections. Even when the object is moving and the drone is moving, it is able to detect properly. This is just to establish the complete chain, right from data collection, then data preparation, model training, then model deployment and testing. So these things are tested and actually tested on underwater images. You can see in different lighting conditions, with light and without light, still it is able to detect with good amount of accuracies. So coming to the detections on ML and side scan sonar, the basically challenge is to construct the image right from the sonar data. So what happens is India doesn't have the technology of developing its own side scan sonar. So mostly we import. So the company, the OEM who supplies the side scan sonar, they gave with some kind of application software, which you can run on PC and generate images. The data is given to it. But that solution is not suitable for us, because as our AUV is moving, we should be able to detect autonomously. So that was major challenge, because as the AUV is moving, it will be getting sonar pings, and you need to construct images on the fly. So that was one of the challenge. Maybe 10. I think we will continue. 5 minutes, 10 minutes. Then the second challenge was implementing these algorithms on embedded hardware and doing inference on in real time, basically. So the data comes from side scan sonar. We do certain kind of pre-processing, because vehicle will be doing certain kind of rolling and pitching. So we need to compensate those dynamics also. Then we do the image formation. Then we do certain kind of pre-processing. Then that pre-processed image will put to the detection algorithm, which will be detecting whether the mine is present or not. So this is how it looks like. With 100 pings, your image looks like this. Then with 200 pings, with 500 pings, because as the AUV moves, you collect more pings and append to the image. So it looks like this. So even it's very difficult for a human to identify whether mine is present or not. So this is how it looks. Underwater mine, when it is scanned with side scan sonar, it looks like this. So this is a cylindrical shape. That was like a trapezoid shape. This is cylindrical shape. So there are the comparison of different models. I think already I have mentioned earlier. Then we did different experiments with different hyperparameters by changing different optimizations, different learning rates, all these things. We tried ADAM and SGD also, madam. Stochastic gradient descent. SGD is giving good results compared to the ADAM optimizer. Yes. And these are detection results. This is, on detection and static images. You have the model, you take the image, static image, and feed to the model whether it is able to detect or not. These are all the detection results. This is one experiment we did. Basically, we mounted this sonar on a moving platform. We deployed a mine on the bottom, and the data is directly coming onto our evaluation board, because by that time our actual hardware is not ready. So just to see in dynamic situation whether we are able to get the data properly, process the data, construct the images or not, then doing detections or not. So that was established a second level. There are the detection results basically. So if you see any, so it's very difficult to identify or distinguish between this object and any of these other shadows. So here also the algorithm is able to precisely identify with almost like 85% accuracy, because if you see these shadows, they also look like mine only. So the combination is very important here. The highlight portion is the shadow. So if you take the only shadow as a feature, then there is chance of like misclassification. So this is tested on harbor. So if you see that this is on still water, like in our tank, the same sonar with same object looks like this. But when you go to the actual environment like harbor, so that images becomes like this. So the variation in the data is very important, and you need to collect more data from the test site or the place where you deploy your model, because lab level data is totally different compared to the actuals. So this is one video, like this is a AEV which I was talking about, a man-portable AEV equipped with side scan sonar. This is the side scan sonar sensor. We did certain experiments in our lab. This is in tank waters only. So as it moves, it will be transmitting and pinging. It will accumulate those pings, construct images and detections. Mine is placed somewhere here, which is not visible. it's done, we collect the vehicle again. We just download the data and see whether detections are happening or not. So these are the detections basically. So we have measured the time, like image construction is taking around 38 milliseconds. So altogether it is around 93, 95 milliseconds on average, which you are able to get 11 frames per second. Because your frame rate is low, you will always miss the object because your vehicle will be moving with certain velocity. So your processing or inference time is also very important here. Then coming to the tracking, because we have multiple set of data, every day train, then compare with earlier results, training results and all. So always better to employ tools like TensorBoard, where it can take multiple logs. You can always readily compare between different data sets. You change a certain parameter, then how your accuracies or your loss curve is varying. The other tool is like weights and bias, but that is mostly on web. You need to connect to the web. Where a TensorBoard we can run on workstation without internet connection also. So these are the very like some of the important curves to evaluate your detection model. So then once the model is trained, we don't deploy as it is. We do certain kind of optimization. The popular tool is TensorRT, which is a library from NVIDIA. What it does is, because ultimately the trained model is combination of your weights and biases. So it will try to prune the model by removing certain weights and biases, basically to increase the performance. And we also do the quantization, like mostly any weight and bias is represented as a 32-bit floating point number. So we can convert into int 16 or int 18. So here the drawback is you will be losing some 3 to 5% of accuracy, but it will your inference speed will increase. So it's again trade-off. So TensorRT can take a model from any of the popular machine learning frameworks, and it will convert into a engine file which can run on any of these devices. So this is the actual, the total flow. We take the data, then we do the model building. Once we are satisfied that the model is good, the data is good, then we go for training. Once we are satisfied with the training, then we go for model conversion by employing TensorRT kind of thing. Then ultimately we deploy. So what we do here is our training, everything happens with, that development happens with Python as the underlying language. But ultimately when we deploy onto the device, we are using C++ to have the better speed. Because compared to Python, C++ is better. So this is the ultimate hardware which we realized, which will be actually sitting on the vehicle. Because these hardwares are employed with GPUs which are power hungry. So we need to take care of heat dissipation. So we put certain kind of heat dissipation handling things. So just coming to the conclusion, I think the recent advances in computing platforms and the large availability of data, which is propelling the deep learning methods, and the quality of data is always plays a major role in our performance levels of any deep learning model. And always the open source based detection models are good point to start. So these models are widely employed in most of the now unmanned systems, particularly in military applications. So mostly people are trying to automate these things by employing these machine learning models, which otherwise traditionally done by humans. So that's the end of my talk. So any things which I can answer. I hope I conveyed something useful to you. Which YOLO. YOLO we tried with YOLO 8, YOLO X and YOLO 5 also. But because it is small vehicle, hardly 30 kgs, it won't have that much of influence on the pressure. Yeah, it's very less. Yes. It cannot cross that threshold. Yes. Anything? You can write to me anytime. I mean, anything which I can help.